Alright, welcome back. Today we're going to talk about finite models, which is really the basis of most testing outdone in the real world for software engineering. A model is really just a theoretical representation of either a program that does exist or something that does exist or something that you intend to create. And being a model, it's usually some type of approximation. One of the greatest benefits is that since it doesn't exist yet, we can actually decide how much resolution or granularity we want in our models in order to quickly get a result that we're looking for or get a result that we need. So up to here we've done chapters 1 through 4, which has been kind of a marathon. Now we're just going to spend one whole week on chapter 5. That's because finite models, while in general are pretty simple, are very, very important to understand. So please take the time to read through chapter 5 and understand it thoroughly. I'm going to try and help you a little with these slides. Also, another reason I gave you the proposal last week, and I want to make sure you do have some extra time in order to look around and actually choose an open source project in order to add to. So please make sure you get started on that because that due date is coming up September 22nd. All right, well, we'll go ahead and get started with finite models. Really, we need to learn that they are an abstraction of something we intend to create or something that already does exist. And then we're going to talk about the specific models that we use for software engineering, namely control flow, and call graphs, and finite state machines. All right, some properties of these models. Hopefully this is intuitive, but we'll go through it. First off, you want your model to be small. You don't want your model to be more complex than the actual thing, because if it was more complex, you'd just build it. So you want your model to be compact and small, something that you can build quickly and actually get something from. You want it to be predictive. Mainly, you want it to always give you a result. You don't want it to be inconsistent and giving you different things. You want it to be semantically meaningful. In other words, it has to have enough resolution so that it actually gives you a result that is meaningful to what you want. It also needs to be sufficiently general, so you want to be able to perform some analysis on it, but not so overly complex that it's basically impractical. Hopefully these are intuitive. If not, please email me. Quick refresh. Hopefully in undergrad you at least have talked about graphs. So a graph is a set of nodes. Depicted here, you have a circle A, circle B, circle C, those are your nodes, and then you have edges, which is basically a connection from one node to another. So here we have A to B, A to C, and another connection from C to A. So this is one representation that's done pictorially, that's pretty intuitive for us. On the left is how it's usually stored in a machine. You have your nodes as well as the edges, so you have edge A to B, A to C, and then C to A. Note there's other ways to depicted over here on the right. This is the same thing. You have A here, left is B, and then A goes to C and then back to A. Might be a little better example of a flow graph. So we're going to go through these again. Notice that these nodes don't necessarily have to be a single statement of code. Well, they can be a single statement of code. That's actually what we're trying to state here. So one node may be one line of code here and then points to the next line of code, A through f of x. And then you connect it saying that you go from A to B because one line of code precedes the next line of code. And so you could actually break it out for each line of code. Another way you could use this model is in object-oriented programming. You might have each node represent a class. And this is an example of multidimensional graph because each node might have a sub-graph, so to speak, inside of it. And there's different ways to depict the relationships, which is why it's multidimensional. In general, we're going to be looking at the other type of graph over here, where you have different nodes plugging or pointing to one another. One last thing I want to touch base on. I don't think the slide does a good way of explaining it, but we don't necessarily have to make each node represent one single line. We can actually group them together, which will help us immensely on simplifying a control flow graph. So each node might represent a set of lines of code, and that way it'll be simpler. And this is what I'm talking about earlier with the resolution or granularity. Maybe a node can represent up to 10 lines of code so that you can actually get you can actually see the whole control flow graph and actually do some analysis. Otherwise it would become too impractical. But before I talk about a little more about that, about what might look like, I gave a number out there of just maybe 10 lines of code. In reality, we usually use something called basic blocks. If you recall from your compiler class, hopefully you took one. If not, a basic block is simply the maximal program region with a single entry and single exit point. Literally what that means is it's the longest sequential lines of code that don't have control break in it. So it doesn't have an if statement, doesn't have a while, doesn't have a for loop. In general, it doesn't have a function call, but that depends on your control flow graph. It doesn't have any way to jump out of those lines of code, so it also doesn't have a go-to. It makes a lot of sense to group these together because once you enter it, you have to execute all those lines of code before you exit. So this is a very common way to group code. And a directed edge is a possibility that the program proceeds from one to another. So if it's statement, there might be one place to go for if it's true and another place if it's false. So here on the right is an example of a control flow graph from the left. Although some of these arrows are not coming out well, so my apologies on that. Usually B1 is the entry point, so that's up here, not labeled. B2, notice B2 contains char last equals argstring.char at 0, string buffer, creating the string buffer, and the first part of the for loop. The reason why that makes sense is that once you started this command, you are going to execute all the way to int cidx, no matter what, because there's no other control flow there. There's no way to jump out. And then after that, on B3, it actually executes cidx is less than argstring.link, so it's actually doing a check. At B3, if it's false, and normally this for loop is false, you go to the return statement. So B3 false, don't see the arrow here, but it'll go all the way down here to B8, which is the return block. But if it's true, then it's going to jump to the inside of the code, which we start at B4. Notice that's the first line, ch equal arg.str char at cidx, and it will execute the first if statement, evaluating it. Recall that C in Java, this is Java code, does short circuiting. So on the or, it's going to execute first that command or the first line of code to see if it's true. Because if it is true, then it's going to go directly to the inside of the code here with arg_buff.append, which is B6. Otherwise, it's going to execute another basic block, last does not equal \n. And if that one is also false, notice that it would jump down to B7, which is the incrementation of cidx. Otherwise, if it's true, then it would go back to B6. And B6 are just the commands inside the if statement. And once that one is done, it goes to B7 cidx. And you don't see the arrow here, but that arrow comes all the way back up, back to B3. And so in this example, we can actually get rid of the code and look at it from just basic blocks 1 through 8 with a different control flow. A terminology you won't see very often, probably outside this book, linear code sequence and jump. This is really just telling you about the paths. So if you start at entry and you want to get to JX, well, you're going to execute B1, B2, B3. If you want to get to JT, you'll be executing those. Entry to JE is those. Entry to JL is those guys. If you're at JX, notice it could be after this, go B8 to the return. Or if you're at JL, notice that this code sequence, you can go back up to B3, B4 to get to JT. And then JL again to get to JE, JL back to JL as well. Notice that there's a couple more entries that you need to get here because if you're at JT, what can you do to get to another jump or label over here? This is just to show you all the possible paths. Now you're probably thinking this is very tedious to write out, but the point of this is that you're going to be having a computer do this so it can do some static analysis of your program. So right back here, your static analysis tool can look at basic blocks. Now we're looking at the different paths in order to see what control sequence can there be. Notice what's nice is once you have JL to JL, then you know what the loop is. So you actually have found the loop here by creating these linear code sequence and jumps. All right, into a procedural control flow graph. Beforehand, I was talking about how you can have your basic block have function calls or not have a function call. So interprocedural, your edges are going to actually represent the calls. So for example, over here on the left, we have Java code. If you want to, since you're watching a video, do pause and take a quick look at this, but I'm going to go ahead. If you're over here on a.check, notice that a.check is called from main, creates a new a and calls .check. So a.check's down here. First thing it does is it creates c, myc, c.factory s, so it's calling a function right here. So a.check depends on this factory function call up here. Then it's also going to call myc.foo. Notice that it's a new kind. We're passing it s, so it's going to pass in, create a new s. c.foo, because if you look down here to s, which extends c, it's actually let's see, c, calling it c, so it's going to call c.foo in this Java code, and then it will also depend on s.foo in case that's what's actually it wants to call. But since, yeah, because over here is extending it or replacing it. So notice that a.check depends on these three because it could be calling any one of them. If you look technically at the code, this guy will not be called, but you may not always be able to decipher that when you're doing a static analyzer. There, it never occurred in the execution. So you can have context insensitive or sensitive call graphs. All this is saying is that, hey, you got main calls c.foo and c bar, and knows that both foo and bar can call depends. So main call foo, which goes back to depends. Bar can also call depends. If you're sensitive, then you want to depict that the one from foo is a little different than the one from c.bar, even though they're very similar parameters. Okay, why would we want to do the sensitive route? Well, that would give us a more thorough examination of the possible combinations that are out there. But why don't we want to do the insensitive? Well, if you do the context sensitive, A can call B or C, and then C, maybe B and C can call either D or E. Well, then D or E could call G or F, and notice that there's a lot of different contexts that can come out from this. So hopefully if you remember from data structures that this is exponential growth. In other words, 1, 2, 4, 8, 16, 32, 64 is going to grow extremely fast, which is why your insensitive call graph will actually eliminate this, because in the insensitive version you just have A through J, which is what, 2, 4, 6, 8, 10, about 10 entries as opposed to 16 here. And when you add more, it would only get worse with the sensitive control flow graph. Alright, so we talked about the control flow graph. Make sure you do review it if any of that was semi-confusing, because that is used a lot throughout, not just compilers, but when doing static code analyzer, because a static code analyzer is first going to run the front end of compiler. So it's very important to understand that in the beginning. Another way to think of this is using a Mealy machine, which if you're on different nodes, so we label those E, W, I, and D over here, and we have different operations depending on what input you see. So if you're an E and you see a line feed, then you're going to emit the line feed and then go back to E. If you see a carriage return, emit the carriage return. Actually, you're going to go down to I. That looks like a mistype there. That should be an I. If you see an EOF, well, you're not going to do anything. You're just done. And then any other character, that's what this picture should be. Wow, this graph is bad. You want to emit that character, and you're back within W. And then W could follow the same thing. You find a line feed, go back to E, carriage return would send you back to I because you're looking for the DOS elf. By this program is a way to translate DOS commands, DOS files into Unix files, and so forth and so on. So this is really just telling you about all the different translations, which is a picture, which is a table showing you what's on the left. There are many different models here. Notice that if you're actually going to do this before programming, you could come up with your properties, maybe come up with a finite state model of some sort, and then come out with your program afterwards. So the point here is the model satisfies the specification, and then the model is syntactically well formed, consistent, and complete. Then you have a program. The model can accurately represent the program. So it has this intermediate property. which actually at least provides you with some information before actually coding the entire thing. And this can be very useful if you're trying to figure out why your final program is not working, or if all of a sudden your program seems to be working fine, but it's not giving the results you want. Maybe the model has an error in it, and this can help you see or review those errors. All right, abstraction function. It's interesting they call it this. Really, we're just talking about the Mealy machine. Take this code, can turn into this type of Mealy machine, or you can look at it from these lines of code as well. All right, hopefully you can see that model is much simpler than the program, although a model must be, in general, is produced by a human. Of course, you have to produce a program anyway, so a model is really not changing it too much, except that it's not an actual program, but on the flip side, it should be easier to create. You must make it sufficiently detailed to be useful, but don't make it overly complex, because otherwise you might as well just write the program. Notice that control flow graphs are usually built from software. That's when you have a piece of code, the static code analyzer is going to create this control flow graph. The finite state machine, on the other hand, can be built before the software to document the intended behavior. And what's nice about that is once you have your model, you can probably have someone else sit down and make sure that semantically the model makes sense and actually matches what your specifications are. And then the programmer can be working from that model to make sure he actually codes it up correctly. Of course, very few programs nowadays do it that way, but it's important from a historical standpoint to see what's been going on as we move forward. All right, that's it for Chapter 5. I'll be putting up the homework momentarily. Make sure you get started on the homework as well as looking for a program for your proposal. It's very, very important that you start looking now for a program or an open source project that you wish to submit or work on.